Hey everyone, and welcome. Today, we're going to demystify three words you hear all the time: work, energy, and power. Now, we use them in everyday life, but in physics, well, they have super specific meanings that might just surprise you. So let's jump right in.
First on the list, work. So when I say hard work, what pops into your head? Cramming for a final exam? Or maybe trying with all your might to push a giant boulder? Well, here's the crazy part. In the world of physics, believe it or not, neither of those things counts as work. The real scientific definition is a whole lot stricter. And honestly, it's going to change the way you look at things.
So here's our game plan for today. We're going to start by nailing down what work really is according to science. Then, we'll explore its connection to energy and break that down into two main types. After that, we'll uncover the one unbreakable law that runs the whole show. And finally, we'll talk about power, which is really all about speed.
All right, part one, what work really is. I want you to try and forget what you think you know for a minute. In physics, it all boils down to two simple conditions, two rules you just can't ignore.
And here they are. For work to actually be done, you need two things to happen. First, you've got to apply a force to something, simple enough. But second, and this is the absolute key, that something has to move. It has to be displaced. If it doesn't move, no work is done. End of story.
So let's go back to those examples. Pushing a huge rock that won't budge? You're applying force for sure, but the displacement is zero, so that's no work. Holding a heavy bag of groceries? You're using force to hold it up, but you're standing still. Again, no displacement, no work. And studying? That's all happening inside your brain. No external force is moving an object. The rule is simple. If nothing moves, no scientific work is getting done.
And of course, in physics, there's always a formula, right? Well, this one's pretty straightforward. Work, which we represent with a W, is simply the force F multiplied by the distance it moves, S. That's it. And the unit we use to measure all this is the joule. So 1 joule is basically the amount of work it takes to push something with 1 newton of force for 1 meter.
Now, here's where it gets really cool. Work isn't always a positive thing. See, if you pull a toy car forward, your force and the car's motion are in the same direction. We call that positive work. But think about lifting something heavy. You're applying an upward force to make it go up. But at the same exact time, gravity is pulling down. Since gravity's force is fighting the motion, we actually say that gravity is doing negative work. So yeah, direction is everything.
And this leads us perfectly to the next big question. If work needs a force to make something move, where does the oomph for that force come from? Well, the answer is energy.
In physics, the simplest way to think about energy is just as the capacity to do work. It's like the currency you have to spend to get things done. To do work on an object, you have to give up some of your energy. The thing doing the work loses energy, and the thing that has work done on it gains that energy. It's a simple transfer, a direct exchange.
But energy is a pretty big word. In mechanics, we like to focus on two major forms: the energy something has because it's moving, and the energy it has because of where it is. Let's meet the two stars of the show: kinetic and potential energy. Kinetic energy is the energy of movement. A speeding train, a flying bird, a gust of wind. If it's moving, it's got kinetic energy. And as you can see from the formula, it all depends on its mass and its velocity. But pay close attention to that little squared symbol on the velocity. That's a huge deal. It means that if you double an object's speed, you actually give it 4 times the kinetic energy. Potential energy, on the other hand, is stored energy. It's the energy that's just waiting to be used because of an object's position or its shape. A classic example is gravitational potential energy. The higher up you lift a book, the more work you have to do against gravity, and all that work gets stored in the book as potential energy. And this image of a bow and arrow is the perfect example of potential energy stored in an object's shape. As you pull back that bowstring, you're literally loading it with potential energy. You're doing work, and the bow is storing it. The second you let go, whoosh, all that stored potential energy instantly converts into kinetic energy, and that arrow takes off.
So we can see energy changing forms, from potential to kinetic. But this transformation isn't just happening randomly. No, it's following one of the most fundamental, most important, absolutely unbreakable laws in all of science.
And this is it, the law of conservation of energy. It's an absolute cosmic rule. You cannot create energy out of thin air, and you can't just make it vanish. The only thing you can do is change it from one form into another.
The total amount of energy in a closed system will always stay the same.
Let's make this crystal clear with a falling ball. Imagine you're holding a ball high up in the air. Right now, it's not moving, so its kinetic energy is 0. But because of its height, it has the maximum potential to do work. All of its energy is potential energy.
Now, you let it go. As it falls, its height is decreasing, so its potential energy is going down. But where does that energy go? It doesn't just disappear. It transforms into kinetic energy, making the ball go faster and faster. But if you were to add up the potential and kinetic energy at any point, the total would be exactly the same. Finally, right before the ball hits the ground, its height is basically 0, so its potential energy is gone. And all of that starting potential energy has been converted into kinetic energy. The ball is at its fastest speed, with the maximum possible kinetic energy. The total energy was conserved every step of the way. Okay, so we've covered work and we've covered energy. But there's one final piece of this puzzle. You see, doing a bunch of work is one thing, but how fast you do it, well, that's a completely different measurement. And that's where power comes in.
Power is simply the rate at which work gets done. It's all about how much work you can do, or how much energy you can transfer in a certain amount of time. The unit for power is the watt, and yep, it's the very same watt you see on your light bulbs. A 100-watt bulb is just transferring 100 joules of electrical energy into light and heat every single second.
This chart makes it super clear. We've got two girls, A and B. They both climbed the same rope to the same height, which means they did the exact same amount of work. But girl A zipped up there in only 20 seconds, while girl B took 50 seconds. Because girl A did the same work in less time, her power output was way higher, 160 watts compared to just 64. Same work, different power. And that brings us right back to where we started. I want to leave you with one final thought to chew on. We established that pushing on a stationary wall does 0 scientific work because there's no displacement. But you still get tired, right? You're sweating, your muscles are burning, you are definitely using up energy. So if no work is being done on the wall, where does all that energy you're burning actually go? Something to think about. Thanks for tuning in.